Okay, we're going to continue on with our two-source interference that we really started in the last video and see if we can sort of look a little more at the geometry and how to solve this stuff. Now, we went over it a little bit last time. It can get a little confusing sometimes, but we'll see what we can do as sort of we can put some ideas together. So we talked about how there's maximums and minimums and, these big parts in the middle, the big ripples stuff, that's maximums. Those are called the antinodes. And there's certain areas where there's nothing at all, and those are called the nodes or minimums. So let's sort of look at how this works a little bit. Now I'm going to take a location. I'm going to take a location right here. Okay. Now that's at a maximum location, no doubt about it. And if I could actually see the individual waves, you can't, but if you could, if I would do like this, and then I'm going to draw another one like this, if I could actually see the waves from there to there and there to there, and I can even draw the actual waves, maybe something like, something like this from the two sources. That's at a maximum. Now, the reason it's a maximum is if I could, I'm going to bring the wave from that red point right there, there's one wave. Maybe that's what the wave looks like from one source. If I could see the other wave from the other source, it would look like this as well. And everything is perfectly synchronized. That's why you have really big waves. The crests are matching up with crests. The troughs are matching up with troughs. Everything matches up at that location, and that's why it's a really, really, really good wave. And that would be true at any maximum location. Maybe look at a different location I know is a maximum. Maybe right here. Okay, maybe right over here somewhere. That's also a maximum location. Okay, actually, let's move that one around a little bit. Let's move it over here. There's also a maximum location right there. Okay, and if I could measure the distances from that source and from that source, obviously one source is closer than the other. But if I could actually see the individual waves, maybe this is what the wave looks like from the closer source, and this is the wave from the farther source, they would still be perfectly synchronized with each other. That's why it's a maximum. A crest is still matching with a crest, a trough is still matching with a trough, and that's why it's such really high waves. Well, let's take a different place. Okay, maybe a place that's a minimum, maybe a place like over here somewhere, that's a minimum location right there. And if I could, again, do my distances, that distance from there to there, and that distance from there to there, my waves aren't going to match up like they did with my maximums, like the orange and the red one, and that's why it's a minimum. If I could see the waves, maybe this is the wave from the top source, the further one, and maybe this is the wave from the bottom one. They are not going to match up like this. Crests and troughs are not matching up. It must look something like this, where instead of crest on crest, I've got crest on trough, cancels. Trough on crest, cancels. That's what it would look like at this location. So it's kind of interesting how this type of thing actually works. These guys, the orange guys up here, your wavelengths, these guys actually match. These guys over here, the wavelengths match. And that's why both of these guys are maximums, because their wavelengths are perfectly matching, crest on crest, trough and trough. Even if I would take the red one, or the orange, let's do the orange one, it's a little bit easier to grab over here. Even if I moved it over, like this, it would still match crest on crest. So I can actually move this one wavelength either way, or two wavelengths, or three wavelengths. As long as I move it a full wavelength, it's going to be a perfect match. So the wavelengths match, you get a maximum every single time. This little light purple guy doesn't work that way. Here, down there, the wavelengths don't match. Okay, that's why this is not a mix, it's a minimum. Okay, this is why that right there is going to be a minimum. Okay, because again, if I would move this, this is what it would be. If it was perfectly matched like this, that'd be a maximum, but it's not a maximum. It's been moved over, but it hasn't been moved over a whole wavelength. It's been moved over half a wavelength. So you shift it by half a wavelength, you get a minimum. So this guy is a half wavelength off, so to speak, and that's what makes it a minimum. So when you can have different distances, that's fine. But if the distances are bigger or smaller by 1 wavelength, 2 wavelengths, 3 wavelengths, they will still match. If the distance is a half wavelength off, that's a minimum. And that's how you can determine whether or not a point is going to be a maximum or minimum based on the orientation. Okay, so I'm going to sort of show you how this works a little bit. So to solve this type of question, to figure out if good waves, bad waves, there's a couple things you got to ask yourself. One is, how many wavelengths away from the sources? Like, how many wavelengths are you away from one source or the other source? And you got to compare them. So how many wavelengths away you are from the sources, that's important. And then you have to compare those wavelengths. Do they actually match up? Are they synchronized? So let's sort of show you how this would actually work. Suppose we have the situation here. Let's use this one right here. And let's suppose we're giving off, we're going to give off 4 meter waves. So these things are giving off waves that are 4 meters long. And you position yourself, doesn't matter where, let's say you are over here. Now we can tell it's a maximum position, no problem, just by looking at the diagram. But let's say you measure your distances, and that's what you need to do. So we measure this distance from here to here, how far away you are from there to there, and we need to measure this distance from there to there. Okay, so suppose I measure those distances, and this is often called source 1, and be source 2, doesn't matter. From source 1, let's say that you are 16 meters away from source number 1, and suppose from source number 2, you are 24 meters away. Okay, now you want to figure out how many wavelengths actually match up nicely. So let's see. What we want to do is we want to find out, obviously source 2 is further away. And if we do that, 24 take away 16 is 8 meters. So 1 is 8 meters farther. Now, what I need to know is if those waves go that extra 8 meters, will they actually match after an extra 8 meter distance? That's what I want to know. Well, let's find out. I have an 8 meter extra distance. I have 4 meter long waves. Let's see if they would fit. If I do that 8 meters and I divide it by the 4 meter wavelength from right there, I can find out that it's actually 2 wavelengths farther. If it's exactly 2 wavelengths farther, it's going to perfectly match up, and that's why that's going to be a maximum. It's going to be perfectly synchronized. The crest is going to move an extra 2 crests along and still be perfectly synchronized. So this is going to be perfect. This is exactly 2. That's going to be a maximum. Okay, so let's look mathematically what we did here. In order to solve this, the first thing we did is we took our 2 distances and we subtracted them. That's what we want to do. We want to take those 2 distances and we want to subtract them. And that's what gave us the 8. Then what we wanted to do is find out how many waves fit in that difference. And that's right here. We divided that by the 4 meter wavelength. And then we find out what we get. And that's exactly how you do the calculation for something like this. Okay, so let's work with this a little bit. Let's clean this up. We'll get rid of a few things here, and we can try another one. Okay, so the expression that we just sort of put together there is really straightforward. You've got S1 minus S2 divided by the wavelength. We see how much farther one source is, and then we see how many waves will fit in there. Now, you'll often see absolute value around there because it doesn't matter if it's positive or negative, but you'll often see this. Okay, so let's take a different location. Okay, let's take this one right here. Okay, suppose you have something right there, and you measure your 2 distances. So we measure this distance, and we measure this distance. And I'll just write right on here. Suppose we measure this distance. This is going to be, well, let's make up numbers, doesn't make any difference. Let's say that is 7 meters, and this one here is 15 meters. Now I want to know what kind of waves I'm going to get. Well, I do the same thing I did before. I will do the 15 take away 7. I subtract those two, and I'll divide it by the wavelength of 4 meters. So 8 take away 7, or 4, 15 take away 7, of course, is 8 divided by 4. It's 2 wavelengths difference, which once again would mean that it's going to be a maximum. Okay, so that's sort of the key. What you want is to get integers at 1 wavelength, 2 wavelengths, 0 wavelengths, 5 wavelengths, 50 wavelengths difference. Then you're going to have a maximum. So if this value right here, if you get any kind of integer, this is going to give you a maximum. Okay, so let's try a different location. Let's try something that's not going to be a maximum. Maybe I go over here, way over here, that far one right there. And I'll do the same type thing. I'm going to measure a couple distances, maybe something like that. I measure this distance over here, like that, and I try and figure things out. Okay, so maybe I measure those 2 distances. Maybe this one over here, it's a lot farther. Let's say this is 32 meter distance, and I do another one over there, and I find out that this is 38 meters distance. All right, so I'll do the same thing. I'll do my S1 minus S2 divided by the wavelength. So I've got 32 take away 38. It doesn't matter what order they're in, because take the absolute value anyway, and I'll divide it by the 4 meters. So absolute value of the numerator, of course, is 6. 6 divided by 4 is 1.5 wavelengths difference. Well, that's a minimum. Okay, you got that 0.5. So instead of the waves being perfectly synchronized, one source is half a wavelength further. So instead of crest on crest, we get crest on trough. So if this gives you an integer plus a half, then this is going to be a minimum. So it's all about finding out, do you get an integer, do you get a whole number, do you get a half, what do you get? Okay, you might get like 1.7, so that'd be like a medium or something like that, or you might get 10.2, which would also be like medium. Whole numbers, maximums, halves, minimums, okay, all depending on how well the waves are synchronized. Okay, so let's try another question based on this type of thing. Okay, so let's try this. Here we got 2 speakers giving off 240 hertz sound waves. For some reason, we got a pig and a dog. Although it looks a little more like a monkey than a dog, but whatever. Piggy and a dog listening to the music, and I want to know which of the 2 actually hears better sound. Okay, and we can use our stuff we're working on to figure this out. Now, first thing I'm going to do is I'm going to find the wavelength of my sound. And wavelength, of course, is speed divided by frequency. And I've got the frequency. And if you remember, speed of sound is around 340. So if I calculate my wavelength of my sound waves, that will come in handy. And this will give me about 1.42 meters for my wavelength. Okay. So now that I know my wavelength, I can use my S1 expression and S2 expression that we used for the previous stuff to figure out what's the quality of each location. So first, I'll start with the pig. So if I do S1 minus S2 absolute value divided by lambda for the pig, I've got my 2 distances, 10 meters away and 12.9 meters away. I can subtract those 2 distances and divide by the wavelength I just found in order to find out what kind of value I get. All right, so if I do that, S1 minus S2 by wavelength, I get a difference of around 2.04 wavelengths difference. So that's really, really, really good. That is almost a perfect maximum because one distance is almost exactly 2 meters farther than the other one. So really good synchronization. Okay, so now let's do the same thing for the dog. I'll do S1 minus S2 lambda for the dog and see what he gets. Okay, and for him I get around 3.45. So that's terrible because that's almost a minimum. That's almost 3.5. 3.5 would be perfect minimum. That half is what you don't want. So definitely almost exactly a minimum. Okay, so it looks like our piggy over here is going to hear the better sound. So whole number good. Half bad. If you had like 3.7 or 3.8, at least be medium sound, so like medium waves and stuff like that. But halves minimum, whole numbers maximum, piggy's really close to a maximum, doggy's really, really close to a minimum.